My presentation is going to be about hydrogen, specifically in the context of Phast and Safeti, although I will mention KFX during the process. So we're very often asked about hydrogen and whether a user can use it in Phast and Safeti. And of course, the very simple answer is yes, because it's available as one of the dipper materials, and you can select it and use it just like any other material in Phast and Safeti. However, it is a rather extreme material, and it's a fair question to say, well, you know, how good is Safeti and Phast for modeling hydrogen, and especially in the light of research in recent years. When Phast and Safeti were first developed, to my knowledge, there was very little in the way of data and models that focused on hydrogen. It was more focusing on hydrocarbons. So the models in Phast and Safeti are largely derived from hydrocarbon data. So I'm going to talk about different aspects of modeling hydrogen in Phast and Safeti, covering discharge, dispersion, a little bit on liquid, jet fires, explosions, and then finally risk. That's the first part of the presentation, and then I'm going to move on to just some more basic do's and don'ts with hydrogen, and that comes at the end. So hydrogen occupies this very special place in the periodic table. It's in pole position. It's the lightest element. And it's of particular interest because it's seen as vitally important in the energy transition to carbon neutral fuels. And there are many benefits to society, but safety is a big concern. And as I already mentioned, there's a lot of recent publication researches. So the very interesting things about hydrogen is its physical properties. It has an extremely low boiling point. And then in terms of hazards, it has a very wide range of flammability. So it has a very high UFL. And the plot on the right there shows the two things. It shows that the energy required to ignite hydrogen is much lower over a wide range of concentrations than typically methane or propane, and also it has an extremely wide range of flammability. So this makes it stand apart somewhat from the standard hydrocarbons. It also has a really high flame speed, and this comes into particularly the explosion modeling. And it also has a very high sonic velocity and of around 1200 meters per second. And then we have to question how good is the discharge modeling, how good is the dispersion modeling, and also any fire that comes after that. So we are actually looking at a range of hydrogen aspects in our modeling. It is work in progress, so I don't have any definitive answers for you today. But as a user, it may be interesting to know of various aspects of Phast and Safeti that may be quite good, and areas which maybe need a bit more care when you look at the results. So this diagram on the right, the block diagram, shows the model. It's our normal model linking slide from the training materials, and it shows in yellow and orange areas of the modeling which you may question when it comes to hydrogen. So on the left-hand side, very much in the risk domain, we're thinking about frequency and immediate ignition probability. The next block there, releases in buildings. Hydrogen is obviously very buoyant. What's it going to do in a building, and are our in-building models applicable? It has this really extreme velocity, so is that going to affect the discharge modeling? And then we come to liquid hydrogen. What about all the aspects of liquid modeling? Rain out, pool spreading and so on. They're not validated for hydrogen. And there's also the question of, is the very low temperature of the hydrogen going to affect the air and cause some strange effects there with solidification of elements of air? So that's in orange because it's probably the most uncertain area. And then moving further over to the right, we've got jet fires and potentially explosions as well. So what about hydrogen and those effects? So starting at the beginning, looking at the physical properties of hydrogen. As I mentioned, we use DIPPER for the basic information about the physical properties of hydrogen. And then we use different equations of state, where Suave-Redlich-Kwong is the default equation of state. And the question is, how good a job does that do for hydrogen? And this compressibility chart here compares reference values by the American NIST group with our predictions using the Suave-Redlich-Kwong equation of state. And we can see that the trends are quite well represented with higher compressibility factors at higher pressures and lower temperatures. So the trends are very good. There is an offset there, and it seems systematically around 5%. We're a bit too high in compressibility factor using the Suave-Redlich-Kwong. So our densities may be predicted to be too low in vessels and pipes. So we're maybe not quite conservative in that respect. So you could compensate for that slightly in your case inputs. Or if we look at the next slide, we can see that if you switch to Peng-Robinson, the trend is slightly the opposite way. So the Peng-Robinson is going to give compressibility factors that are a bit too low. And so you could argue that this is a more conservative choice when modeling source terms. You tend to get probably higher flow rates and higher masses released. You may ask the question, why don't we use a more accurate equation of state? I mean, largely it's because the really accurate ones are very expensive to calculate, so they wouldn't be appropriate for a model like Phast. But there are potentially other equations of state we could consider for hydrogen. So again, that could be work in progress. We're not focusing on that at the moment, but please be aware these options are available to you. So moving on now, we can start thinking about source terms and dispersion. And quite recently, we've done quite a lot of work on the expansion methods in Phast and Safeti, and looking at different options for defining essentially the start of the dispersion. So we call this the final state, but essentially it's the state after the source term finishes and the dispersion starts. And there are various options that people have looked at in the literature, particularly for hydrogen. You're probably going to be looking at high pressure releases. It's going to be shocking as the pressure drops to atmospheric from the actual hole, and there are different ways of approaching that in these models. Now, our most recent work, we've looked at different capping options for the final velocity, and we've changed to an uncapped solution. And the reason for that primarily is this validation here. And you can see that the uncapped model predictions, which are in the green lines, are the best with respect to the validation and the data. So we felt this was strong enough evidence to to set this as the default in Phast and Safeti. So that looks good. But when it comes to liquid hydrogen, it's probably a bigger question. And we've been looking at that as well. And there's actually been quite a lot of work recently on liquid hydrogen. And at DNVGL, we've been quite fortunate to be quite closely involved in quite a bit of this. And I'm going to show you some experiments that were conducted at the DNVGL Spade site, I think last year and the year before. And these are a couple of other joint industry projects where DNVGL have been involved, Safe and Presley. And I think they're still ongoing. I'm not totally sure about that. So the spade atom tests, these are quite large scale, and there was a liquid hydrogen tanker, and the liquid hydrogen was piped using 2-inch pipe to the pad, concrete pad that was going to be used for the experiments, and release directions varied in 2 ways, so either horizontal or downward. And there was particular interest in the downward because this is much more likely to cause some kind of liquid pooling on the ground. Flow rates are approximately 0.8 kilograms per second, so reasonably large scale. And both unignited and ignited releases were performed. And so there's data for discharge, dispersion, potential pooling, and the flammable effects as well. So there's a rich body of experimental data and evidence here, and it's quite exciting to have this to work with. So I'm just going to show you a video, and I'm going to show you different angles. So this is really with the release coming towards you now, and it starts off unignited, and then you'll see it ignite, I believe, approximately 30 meters away from the source. And this is a horizontal test. So bear in mind, this is a horizontal test. So you can see the cloud building up. The ignition occurred, I believe, somewhere near, if you can see this residual combustion, somewhat downwind. So that's one video. Now, if I show it to you from a different angle, this is from behind the release. You see the cloud build up. There's the ignition, and then you can see reasonably clearly the jet, very high velocity jet, and then the buoyant part of the plume going up, and it looks as if there's a crosswind pushing the flame sideways. And then my last one here, I put is more from the side, so you get to see the jet, and then transitioning, as you can see, there's a very high velocity jet, and it transitions to a flammable, a more buoyant part of the plume. And I put this on slow motion, so you'll be able to see it, perhaps hopefully in more detail. So you can see the initial vapor clearing, and I think you can see quite clearly there's a very strong horizontal turbulent jet to start with, and then as the combustion products slow down, buoyancy takes over, and the combustion products and the flame indeed head head up. The results of this have been published. I'll give them the reference there, and we're looking at validation. So far, I mean, we did some calculations as input to the experimental design in terms of the mass flow rates, and it's quite a tricky calculation because we don't know how much the heat transfer potentially along the pipe is going to affect the source term, and whether it's really liquid or already two-phase at the exit to the pipe. But the mass flow rates we predicted are really quite good, so we're quite confident with that. And also the rain out. So the analysis of how much liquid actually rains out is quite complex, but given the complexity, we're predicting a reasonable amount of the rain out. Of course, it's going to tend to evaporate very quickly, but because of the high rates of heat transfer. But at least the amount of rain out can be reasonably predicted. I mean, we're all aware of obviously of limitations here, and it's still early days in terms of validation. There's a lot of data there. We've only really started looking at it. You know, I've already mentioned the heat transfer, the impinging jet on the ground. We only have a very simple representation of the interaction with the ground, so that's likely to be uncertainty around that. With the unignited releases, the potential lift off in the dispersion for a downward facing release, it's we tend not to allow it to lift off because of the various criteria in the UDM, and that can lead to clouds which are too narrow and too tall, and so that's something we need to look at. And again, I've already mentioned the potential condensation and solidification of nitrogen and oxygen, possibly interactions with the pool. There could be a lot of complexity around that. But the initial indication is that for that type of release, these things aren't obviously affecting the the behavior of the fire, particularly importantly. So just moving on now from that focus on those liquid experiments, let's move on to the jet fire, the normal. Let's for the minute just forget about the liquid hydrogen. We're moving on to vapor releases now. And this is some validation we did previously from, again, experiments at Spade for a vapor fire. And these fires were in the range of 1 kilo to 6 kilograms per second, horizontal jet fires. And the pressure is about 60 bars, so quite high pressure. And we get good validation with Phast, and this is where I have to give some advice about some limitations of the current jet fire modelling in Phast, and hopefully give you some practical advice on how to adjust for that. So, the capping settings have changed over different versions of Phast. So the early versions of Phast had 500 meters per second. Then we moved on to a sonic velocity cap, and now we're using uncapped. So for those at that experiment I just showed, this one here, velocities are of the order of 2,000 meters per second, which is above the sonic velocity of about 1,200 meters per second. And what happens if you use the default settings in Phast is that the flame shrinks for horizontal releases. And I'm just going to try and move my mouse here and try and highlight the flame shapes there being shown in the diagram on the right. So for horizontal releases, we use a different correlation to vertical and angled releases. So for horizontal releases, we use the Johnson model, which has this uplift. And for other releases, we use other angles, we use the Chamberlain model. Now, one feature of the Johnson model is the lift-off distance becomes extreme for very high velocity jets. It's possibly that's representing the very high turbulent region of the jet, which could be quite realistic, but there's no radiation emitted from that. And so you can get quite misleading results from the default method in Phast for horizontal releases. Also, another characteristic of the Johnson model is the emissive fraction reduces as well very extremely. So the emissive fraction will go down and down, and you're going to be underestimating the radiation. And the diagram there just shows the difference between switching to the Chamberlain model from the Johnson model and the size of the radiation zone predicted. So our concern is that the default modelling in Phast is not conservative, and that's one of the reasons for giving this presentation. So what can you do about that at the moment? I mean, we are investigating this and looking at various options. I'll say a bit more about that on the following slide. Well, you can switch to the Chamberlain method, and that's available in the parameters. You can do that at a model level. You can also do it at a global parameter level. And that then gives you a much larger flame and addresses one of the weaknesses. It addresses another weakness as well, and that relates to the emissive fraction, and I'll talk more about that on the next slide. And we also recommend increasing the maximum surface emissive power from the default 350. Just put it up to a high value, just so you're not capping the emissive power in a way that we're not confident about at the moment. The emissive fraction, the maximum of 350 is really derived from hydrocarbon experiments. So we are working on this, but these are things you can do in the meantime. Now, once you switch to Chamberlain, you're then using a different emissive fraction correlation. It's a much simpler one, and it means you're going to be using an emissive fraction of 0.11 all the way up to 0.32, just depending on the velocity. So, as I say, it's a simple correlation just based on velocity, which makes it easy to understand. And you can see the range of 0.11 to 0.32 is still quite a large range. Now, when I say very high velocity for 0.11, anything where you've got choke flow under expanded jets is going to be 0.11 with the Chamberlain model, essentially. So 0.32 is really for much lower velocity releases. So if you can think of, for any high pressure releases, the Chamberlain model that's having an emissive fraction of 0.11, that's probably quite a helpful way of looking at it. Now, what I've got here are some diagrams from recent work. There's one by Sandia, and you can see here they've got a correlation for emissive fraction, and it ranges anything from as low as just over 1%, all the way up to, with data, up to 20%, and with their correlation up to 30%. Now, their correlation is not that easy to follow because it's based on this concept down here, which is based on a concept of a residence time. But you could probably set up a spreadsheet and calculate these values yourself. and then you could use this value as input to Phast, or just choose a conservative value for the type of flame you're looking at. Another very interesting publication on the right by Derek Miller of Air Products, and his modeling has identified a difference between horizontal and vertical flames, which we don't fully understand the mechanism behind this, but his correlation has an adjustment for horizontal flames. So again, to be conservative for horizontal flames, it may suggest that emissive fraction should be higher than perhaps the Chamberlain or the Panda correlations, although I believe this does include some horizontal flames as well. So I don't have any hard advice for you, but basically this is a residence time correlation on the left. It suggests that the smaller flames and higher velocity flames have lower emissive fraction. If you use the Chamberlain correlation for flames that are in this range down here, you're going to be very conservative because you'll have a minimum of 0.11 emissive fraction. So if you've got very small flames, you may be overestimating the risks if you use Phast Chamberlain model. On the other hand, a lot of these experiments on the right, they're larger tests. They include quite a lot of lower velocity experiments as well. And you can see there's a trend with mass flux. So obviously the higher velocity releases are on the right, with the lower tending to have a lower emissive fraction, and the lower velocity ones on the left tending to have a higher emissive fraction. And this is somewhat represented by the Chamberlain model. So that's something else to be aware of. So just moving on, this is work we're doing. We're assessing the applicability of these different models and correlations and looking at different options to enhance Phast. We're also using KFX and validating KFX, but also looking to see if we can use KFX to investigate some of these behaviors, particularly understand the behavior that Derek Miller's identified, and also improve our guidance for applying Phast and Safeti for hydrogen jet fires. Just moving on, we have the issue of explosions and how applicable is Phast and Safeti for explosions. And there is this issue that there's a very low minimum ignition energy. And there's also a physical phenomenon with hydrogen known as the Joule-Thomson effect, which can lead to some heating of the final state of the hydrogen. And yet that in itself is not enough to cause ignition. And there's papers on that or publications that discuss that. However, it is more likely to have immediate ignition with hydrogen. The HFSE has a discussion on that, and so we tend to treat it for in risk calculations as having a higher immediate ignition probability than normal hydrocarbons. However, it's not guaranteed to ignite, so it is perfectly feasible to have, and does happen, having delayed ignition of hydrogen. Indeed, you saw that in those liquid hydrogen experiments. So the clouds do tend to be buoyant, but they're not necessarily going to go straight up immediately, and could well develop significant flammable clouds in congested regions and near the ground. And that can lead to various explosion outcomes. And particularly with hydrogen, it's more likely that the whole cloud could detonate, even without significant obstructions. And probably the larger the cloud, the more likely it's going to tend to detonate. There is some evidence of that in the literature. So we do recommend that you consider a detonation as a potential explosion outcome. It's not going to happen every time, but it is a potential explosion outcome. And you can do that in Phast using the unconfined explosion strength. When it comes to risk, we also have options to represent detonation. There is a branch in the event tree that can be activated to look at the to include a detonation outcome in the risk. And there's two criteria to trigger this based on flame speed or characteristics of the obstructed region that the cloud finds. So it's not necessarily always going to detonate. It would detonate if it finds an obstructed region that's going to accelerate the flame enough to detonate the whole cloud. And it's not going to detonate every time. For instance, if the cloud is burning back from an ignition point outside the obstructed region, then it could be deflagrating back to the obstructed region and only detonate in the obstructed region. So there's a fraction of that can be applied to the detonation branch. There's also probably not a well-known feature of Phast, or Safeti rather, that could be used, which is this volume-based method where you can define different probabilities depending on the volume of the obstructed cloud. So this would be a way of adjusting the probabilities depending on the cloud size, which it looks like could be a well justified way of looking at hydrogen clouds and explosions. So here you've got various options in Safeti for dealing with explosions. So that's the modelling side of it in my presentation. I do have some of these do's and don'ts just to finish off with. Now, if you're modelling a vapor hydrogen system, then it's and you've got mixtures of hydrogen with other vapor, then it's fine to add hydrogen to mixtures. So that should be fine, and you should get sensible results. Just be aware, though, that the ignition category will change. So we have this very sort of conservative mixing rule. So if you just put any amount of hydrogen in a mixture, it's going to trigger the immediate ignition probability to high. So an extreme example of that would be if you've got a methane stream which has a low immediate ignition probability, and then you put in 1% of hydrogen, then suddenly it's going to switch to high, and arguably that's too extreme a change. So just please be aware of that. You can change this if you want, but we do get support cases where people are getting discontinuities in modelling and don't understand it. So please be aware of that. But when we come to mixtures and liquid, it's a different story. So if you don't have a multi-component license, then please don't put hydrogen into liquid streams. Although we don't prevent this, it's not a good idea, and it's likely to produce very strange results because we're representing the multi-component phase envelope with a single curve, vapor pressure curve, as per a normal pure component, and this is not realistic for hydrogen when you've got hydrogen in a mixture. If you've got a multi-component add-on license, it should be fine to put hydrogen in a mixture, but we have observed some sort of failures, model failures, which when we've diagnosed it, it's because the hydrogen is such an extreme component in the mixture. The numerics can sort of try and converge down near the boiling point of hydrogen or something like that, and then all the other components don't make sense, and it fails to converge. So if you tried it with 8.23 right now, you'd probably get some model failures. We are working on that, and it's already a lot more robust with 8.4. But it may still lead to some sort of difficult cases. But in theory, it should be fine. You can. We do also now recommend the multiple aerosol when using multi-components. So that's another sort of development we sort of recommend. So that's this is my last slide, just to sort of recap. I've talked a bit about the modelling of hydrogen with Phast and Safeti, and some of the sort of pros and things that seem to be quite good. But I have given you some advice about jet fires and also some don'ts with mixtures, do's and don'ts. And this is work in progress, so hopefully in the near future we'll be able to provide a better model in Phast for hydrogen without you having to worry about it, and giving good validation and comparing well with all recent literature. I've given a couple of useful resources there, and as stated yesterday, I repeat just a reminder that all models are wrong, but some are useful. It's a well-known quote from a very wise man, George Box. So thank you for listening.